Thank you. Thank you very much. Thank you for the invitation to this marvelous place. Today I'm going to talk about experiments and theory protocols which we're devising in Paris together with my PhD, my students, and also with a young colleague Matthew Delbecq, who is going to show up in fact later this afternoon and explain to you other things tomorrow. And on the theory side, we've have the long-standing collaboration with Audrey Cotter, and this is part of a more general collaboration with Igor Rastorza, Sorin Parano, and Wolfgang Wersdorfer. And so the idea is to use ideas about sensing and quantum sensing to probe cosmological objects, such as good candidates for dark matter. So in fact, yes, there are many good reasons to postulate the existence of dark matter in the universe. So I have represented two of these reasons. The first is actually an image. These are actually three superposed images of the bullet cluster here. Optical, X-ray, and gravitational lensing. And in fact, a closer inspection of this image, where you have these different colors, which represent different parts, like the different methods of imaging, show you that, in fact, these kind of purple here parts are actually things which have a gravitational effect, but are outside, what can be observed. And this is believed to be one of the most compelling evidence for the fact that there are things which have a gravitational effect on the big scale objects in the universe, but which we know what it is. So here is actually also the estimated matter energy content of the universe, and from in fact careful study of the microwave cosmic background, you can actually come up with this kind of estimate where essentially everything which we know, so which is called here ordinary matter, is actually only 5% of the elementary constitution, would be 5% of the elementary constitution of the universe, and the rest would be dark matter and dark energy. So the idea of dark matter is that it would be something which would have a non-zero density in the galactic halos, and even at our location in the Milky Way, but it would have an extremely weak interaction with the ordinary light and matter. And it turns out that there is now a very important and very well motivated object which actually would have a mass which would lie in the microwave range. And so this is why now we can be willing to use all the tricks of quantum microwaves to try to probe these particles or fields which are called axions in laboratory experiments. So of course I can't help showing you that this, of course, this is a topic which goes outside the physics community, and in fact even rock bands, they have now their own theories about galactic halos. So this is the the Pearl Jam image of the galactic halo in the Dark Matter Tour 2024. So okay. So, but we want to go beyond what Pearl Jam has just provided to the community. So we would like to try to be a bit more specific, and so let's try to be a bit more specific about one important class of candidates for dark matter, which are called axions. So the axions were proposed in a different context, like from cosmology. They were proposed in high energy physics as a actually solution, an elegant solution for the charge parity conservation for the in the Lagrangian of the standard model. And so essentially the idea is that the Lagrangian of the standard model, tells you that there is a term which actually for which there is no a fundamental reason that it should be zero, but if it was not zero, it would give an electric dipole to the neutron, and the neutron electric dipole has been very strongly constrained to be 0. And so this was a problem. This is one of the failures of the Standard Model. And so in order to reconciliate, like to try to deal with this failure, Pecci and Quinn in 1977 came up with a new field or particle, which was called axion by Wilczek later on, in fact. And this actually would come from a symmetry breaking, which, I have represented here with this Mexican hat potential. And essentially, this would turn this kind of like problematic term in a Lagrangian of the Standard Model as some kind of expectation value of the field, and therefore restore this fundamental symmetry. And so, like after many theoretical developments, it has turned out that if it exists, it would be very light, so it would be somewhere in the microwave range, although there are pretty loose bounds. And it has turned out to be a very good candidate for dark matter, so it's very weakly coupled to everything which we know. So there is a very important consequence of the potential existence of this field is that it would modify, if it exists, Maxwell's equations with very generic arguments. And so, so maybe the Maxwell's equations, as we know, are wrong, and that they would have to be complemented by additional terms. So, which are these 3 terms here. And essentially, here you will have the coupling constant between the axions and the photons. And you see that they have like some specific consequences in the Maxwell-Gauss and the Maxwell, let's say, Ampere equation. And one particular interesting term which can be tested experimentally is this one, which appears more as a current source, which actually would modify, would enter here in this last Maxwell equation. So, of course, you can try to estimate the order of magnitude of this term, and there are these 2 benchmark models here, which are called the KSVZ and DFSZ, and these benchmark models, they tell you the order of magnitude of the kind of powers which you would have to measure in order to test this prediction. And of course, there is no universal value for these powers, but let's say for generic, setups, you always fall into the 10 to the minus 22, 10 to the minus 24 watts. So it's pretty small order of magnitude. And so the question is how to detect such a small correction to Maxwell's equation. In 1983, Pierre Sikivi came with this seminal idea to say, okay, this term can be actually tested in a laboratory experiment. So you can rephrase like this modification to Maxwell's equations as a single magnetoelectric term in the Hamiltonian of the electromagnetic field, which is modulated at a frequency which is just the mass of the axion, so somewhere in the microwave range. And this is the coupling constant here. And so in fact, he said, okay, look, if you make a microwave cavity resonant with what is like the mass of the axion you want to test, and you put this cavity in a pretty strong but accessible for laboratories magnetic field, essentially this term becomes a driving term for the photons in the cavity. So at rest, in fact, the axions, they fill up the cavity with an additional number of photons, which would not be there if the axions were not present. And essentially, you can sketch the process like this. So you essentially convert an axion into a photon in the presence of the magnetic field. And so this essentially fills the cavity. So if you're able to measure very accurately the power coming out of the cavity at the frequency of the cavity, you will be able to tell whether axions exist or not. So there are two problems for this. The first is that if you convert these powers into a number of photons, it's on average is extremely small. It's 10 to the minus 5, 10 to the minus 3. And of course you don't, and in fact the other problem is that it's a needle in a haystack problem because you don't know which mass, I mean like the QCD doesn't tell you where to look for like which mass it should be. It tells you just some loose bounds between, let's say, sub-gigahertz, let's say, to hundreds of gigahertz. So, and so you expect from like astrophysical arguments that the line width will be somewhere in the kilohertz range. And so this is really a pretty narrow line width over this huge span. So what I'm going to try to convey to you today, one of the things is that, in fact, using a magnetic platform, you can in fact, let's say, lift this kind of problem, at least partially, owing to the magnetic field tunability of the magnetic resonance. Okay. And so this, of course, still, I mean, has not stopped people from trying to find signals. And so there are many people who have actually done measurements with microwave cavities, which are, these kind of setups are called heloscopes because you probe the galactic halo. And you can re-represent the limitations of the heloscopes by using a phase space representation of the electromagnetic field of a microwave cavity. So if it's completely at rest, you just have thermal quantum fluctuations for the electromagnetic field. And so the electromagnetic field is centered around 0. And you have this essentially this kind of width here, which represents the uncertainty, so the noise of the field, which if you cool down the system will be limited by quantum noise. So the size of this spot here will be essentially 1 photon. And if an axion is around or is resonant with the cavity, what will happen is that you will essentially shift off-center the electromagnetic field. And of course, this is a completely blown up scale because, in fact, like this is a tiny effect. Nevertheless, but if you integrate, so you're trying to distinguish two almost overlapping Gaussians. Nevertheless, you can try, if you average enough, you will be able to discriminate these two spots. But the price to pay is that you have to average for a long time. And so the fact that this guy here is limited to 1 photon is called the Stern quantum limit. And essentially, this is a substantial slowdown for axion dark matter search because you need to, if you want to scan, even imagine you have means for scanning, this is a substantial slowdown because you have to integrate for a long time to get a signal to noise ratio 1. Okay, so and the reason why this guy is like this is round, like this, you have a spot here, is because the two quadratures of the electromagnetic field are non-commuting variables, so you cannot and so this is why, I mean, you have this thing here. So one kind of you can you say, okay, why not then changing the conjugate variable and trying to find something which would be more favorable to sense this kind of tiny signal, which is much smaller than the quantum fluctuations of the electromagnetic field. And so you can, and so this is kind of something which has can be a priori something you can ask. And so, of course, the question is that you can do two things, which are the variants from each other. You can say, okay, I want to go from the two quadratures, so the in-phase and out-of-phase components of the electromagnetic field. And what if I change to the number and the phase? And by doing this, essentially, you can be willing to measure either one or the other. So either being number, let's say, discriminating, and so and with a completely unknown phase. And so this is what you're doing with single photon detectors. Or as we do in Paris, you can say, okay, no, it doesn't matter to know exactly the number of photons in the cavity, but if, why not trying to measure the phase of the electromagnetic field and trying to find something which will be able to translate the axion amplitude into a phase. And this is why we have chose to do in Paris. So the single photon detecting efforts are, for example, done by the folks in Padova in collaboration with the SACLA people. And so this is the work which has just appeared recently. Katerina Brajo is the first author. Okay, so if we want to do this, one thing which we can think of is that if I want now to translate an amplitude or into a phase, one like a way of doing this is to use an anharmonic cavity, because the anharmonic cavity is actually translated like it has its frequency, which is dependent on the power, and therefore you can be this can be a resource for translating the potential action signal into a phase. And so this is what essentially we have proposed with Audrey Cotter. So essentially the idea is to translate the axion field into a parametric drive of an anharmonic cavity. So the anharmonicity of the cavity here is, this is oscillating, it is, okay. The anharmonicity of the cavity here is actually encoded into this K parameter, which is essentially, this is called, in a jargon, the cross-care term between two modes. One mode is used for storing essentially the action information, and the other mode is used to detect the action information. And so what we propose here, what we find in this by using this trick is that for realistic parameters we can boost the figure of merit of the heloscopes by essentially about 4 to 5 orders of magnitude. So you can reduce the time to detect potential action signals by 4 to 5 orders of magnitude. Okay. And so the other thing is to use a magnetic resonance. And so the idea is to use gyromagnetic modes, so of magnetic insulators. So they can be ferromagnetic, ferrimagnetic, anti-ferromagnetic. It works for like as long as you have the kind of the off-diagonal form for the permeability tensor in these materials. It works for all these materials. And essentially, the idea is that if you have now a ferromagnetic resonance in the game, essentially you will be able to tune now the mass you want to detect with the laboratory magnetic field, which enables you to scan over many orders of magnitude the magnetic resonance. And in addition, if you're dealing with gyromagnetic modes, it has the right symmetry to have a finite, let's say, form factor for the E dot B term, which is the term you want to detect in the corrections of Maxwell's equations. And so again, here, so if you plug in numbers, you expect to have a macroscopic coupling strength with axions, and to have something which can be used practically for axion detection. Okay, so we have started to implement these ideas experimentally. So we have now worked so far on the pathfinder, on the proof of principle of these ideas, using this kind of setup. So you have a three-dimensional copper cavity with an antiferromagnetic crystal here, which is a gadolinium vanadate. And the anharmonicity of this cavity is given by a magnetic field resilient superconducting circuit, which is a Josephson junction made in granular aluminum. Okay. And so the anharmonicity, again, of the granular aluminum quantum circuit gives a resource for photon to frequency conversion, or for a direct measurement, let's say, of the photon number inside the cavity. Okay, so let's see whether we can see already some magnetic field tuning possibilities by doing the spectroscopy of the cavity as a function of the external magnetic field. And if you're measuring the spectroscopy, like the lowest modes of this magnetic insulator cavity hybrid setup, this is what you find. So you find that you have, like, for example, these 4 modes. These are the 2 kind of cavity modes, and these are like 2 gyromagnetic modes. And you see that all these modes, they have a very strong dependence as a function of the magnetic field. So this is a kind of a simplified, let's say, a very simplified phase diagram of the gadolinium vanadate. So around 1.1 Tesla, you have a spin flop transition, and then you get into the ferromagnetic transition. And below this 1.5 Tesla, you're in antiferromagnetic phase. And so this antiferromagnetic phase here is actually around here. Here would be the spin flop. And in fact, we can understand pretty well the antiferromagnetic phase. And so this kind of very strong dispersion is actually what you would expect from the gyromagnetic modes. This is just a witness of the magnetic field dependence of the magnetization, and also the magnetic field dependence of the magnetic resonance. So the spin flop, above the spin flop, we understand not as, like, we don't understand very well, I mean, the dispersion, although we understand it qualitatively. But what is important is to understand an antiferromagnetic region, because this is where we want to use ultimately this setup. And what you see here is that you can have a tunability over, like, of these resonance, which you can over more than 4 gigahertz. And this, if you apply this to heloscopes, this would be 2 orders of magnitude improvement for the magnetic scanning potential of this thing. Okay. And so essentially, now let's see whether we can measure now very small powers by using this power to frequency conversion owing to the anharmonicity of the systems. And essentially, the idea is that now you want to measure accurately the frequency of the anharmonics oscillator in the setup, which turns out to be the superconducting circuits. And so in order to do this, the conventional quantum sensing trick is to do Ramsey interferometry, where essentially you have this pulse sequence on here, in our case, this is nanosecond and microsecond time scales here. So you have this pulse sequence where you have 2 pi-half pulses here, which essentially bring your effective spin on the equatorial plane. You let it evolve, and during this free evolution here, you can actually measure very accurately whether the frequency of your system has changed due to a perturbation. And so you have generate this kind of pattern for when you're measuring as a function of time, and which you understand quantitatively. And essentially now the idea is that you can mimic essentially what an axion would make to your system if it would be it would fill the cavity, and if it would interfere with the photons already present in the cavity. In this case, the signal is this vertical and the horizontal signal, of the Ramsey interference pattern. And it's translated into a vertical signal, which is the phase which you're measuring. And in fact, if you look now as a function of the fictitious axion signal phase, what is happening, you see that you have some wiggling of the pattern of the Ramsey interference. This wiggling, the amplitude of this wiggling, is actually giving you, allowing you to measure directly the equivalent number of photons. And from this, you can make this kind of plots where essentially you look as a function of the perturbation translated into a number of photons, the signal up to the threshold, which is just the noise of your setup. And what you can see here is that you can go down into, with this setup, to the 10 to the minus, let's say 4 to 10 to the minus 5 limit, which is well below the single photon limit, and which is interestingly is kind of the orders of magnitude which I was telling to you about at the beginning. So you can also do this because now you have you can try and probe many different modes in your setup because now you have a direct frequency conversion means with your harmonic setup. And so this is what is happening, what we can do for the sensing for normal photons in another mode. So this is less sensitive, but we can go down to the 10 to the minus 2. Okay. So now, I mean, we can, let's say, try, owing to the fact that like this, the proof of principle works, try to see where we should be given kind of like if we use this setup as compared to existing experiments. And in fact, one of the very interesting aspects is that we would be able to measure extremely fast. So this remains to be proven in our case, but we could actually have the cosmologically relevant sensitivity, so that's now a prediction, on essentially very short time scales, which would allow us to detect axion signals in real time. And so now, if I represent where we would be in the coupling strength mass map, in a single experiment, we will be able to cover a very large, essentially, area, whereas most of the existing helixscopes, they measure a very tiny, let's say, stripe in this phase space. Okay, so as a conclusion, I have shown you that one can use the quantum sensing techniques to probe these cosmological objects. And now this is here, like the data-taking setup, which we have started to work on with Chloé Fruy and Jeanne Bailly, which would have a volume of about 30 cubic centimeter, and we would allow us to probe with a wide mass scanning range this kind of dark matter candidates. Thank you for your attention.